Hello everyone, and welcome to this lecture of Advanced Geodynamics, Theory and Modeling. In the previous lecture, we have discussed the coupling between hydrological and thermal processes. This has led us to hydrothermal equation that we've derived using the principle of conservation of energy, the principle of conservation of mass, and the production of entropy. We've ended up with one equation for the evolution of a fluid pressure in the porous media and the evolution of the temperature field in the porous media, including a term of dissipation here and additional coupling terms related to expansion and adiabatic heating. This was based on Darcy's law and also Fourier's heat flux, which are used in each of these equations. Now, in this lecture, we want to discuss about thermo-mechanical coupling. And thermo-mechanical coupling is really central in geodynamics because it's the foundation to be able to simulate, for example, mantle convection, thermally activated strain localization, and lithosphere dynamics in general. So, for example, we had cases that we've already mentioned in the previous lecture where one may study how strain localizes due to dissipation around heterogeneity in a material which is under deformation. This can generate zones of intense strain, and when one ports such a toy model to the scale of the lithosphere, a model here featuring an oceanic plate and a continental plate, the same process may happen, but now at the scale of the lithosphere, leading to the formation of subduction zones. Thermomechanical processes also matter a lot for understanding subduction and collision processes in a quantitative framework. So these are thermomechanical modeling of subduction and exhumation processes. And they are also very important to understand how the deformation of layered material takes place. Another really interesting example here is continental rifting, because in continental rifting, of course, you do have a strong interaction between thermal processes and mechanical processes. So you see here a lithosphere which has been deformed. This is basically the crust. It's been stretched out, and the isotherms have been advected, heating up the sediments in the middle of the basin here. And with thermomechanical equations, you can also move to the global scale and model plate tectonic on Earth, or even study convection on planets in general. So let's start with discussing the energy. Now we are talking about thermomechanical processes. We will be forced to extend the energy formulation. The internal energy will not be enough. So it matters, but remember this example from the roller coaster. We should formulate a total energy. So we formulate the total energy. It's the sum of all forms of energy in the system, including the microscopic contributions from internal energy and the macroscopic contribution from kinetic and potential energy. In the following, we will only consider kinetic energy. To simplify the derivation, we neglect potential energy for the time being. So that's our reduced equation. E equals U plus E kin. E kin will be V squared divided by 2. So it's an energy in intensive unit per mass. And it's good to have a formulation for the energy, but what matters the most is to have a formulation for the differential of energy. So let's formulate the differential of energy. So we need to take the derivative of this expression here, the total derivative. So we have dE, it will be equal to du. And now we need the derivative of V squared divided by 2. And the derivative of the differential of V squared divided by 2 is simply V product dV. So that's the differential of the total energy to be used in the following slide. In the following, we will consider a single-phase non-porous system. The temperature, the velocity, and the pressure will evolve. One will have to be careful that the velocity here is a vector. We need to construct equation for the evolution of all of these quantities. And to construct this equation, we need to go through a thermodynamic recipe. The equations to be used will be the conservation of the total energy, note E here and Q here being the flux. V is the velocity vector and QV will be the flux of momentum. Here we have the density and the divergence of velocity. You can recognize the mass conservation equation. Of course, for thermodynamical consistency, one needs to add this constraint here that the entropy should be produced during this process. So where to start from? As usual, we start by doing an entropy check, and here we start with the internal energy. Remember from last week we had 3 terms in the internal energy. Here we are going to neglect the chemical coupling terms, so du will be TdS minus PdV, and as we've mentioned before, what we are going to conserve here is not internal energy but total energy, so we can inject this into the differential of total energy. We have TdS minus PdV plus V dV. Now let's work a bit this equation and solve it for ds, for TdS. So TdS is equal to dE plus P dV, and dV is V is 1 over rho, minus V, the velocity vector, times dV. What we can do now is to substitute the volume. dV is d1 over rho. It's equal to minus 1 over rho square times d rho. And then one can use mass conservation to further simplify this term. dV bar is, in the end, 1 over rho divergence of velocity using mass conservation. So we can simplify this equation. TdS will be dE plus P divided by rho, divergence of velocity, minus V times dV. Now, let's multiply everything by density. This will have the effect of cancelling the division by rho that was here, but it introduces rho here, and rho there. So we have rho TdS, and now we can use the entropy balance. Let's keep this equation here and formulate the entropy balance. Rho ds dt plus divergence of entropy flux should be equal to the entropy production term. As usual, we can solve this equation for TQS. This is equal to T rho ds dt plus T divergence of QS. Now we inject the definition of T rho ds dt that we've derived before. So T rho ds dt will be equal to rho dE dt plus P divergence V minus rho V dV dt. And we have the term T times aversion QS. So we have this entire equation for TQS right now. And what are we going to do? We are going to identify the conservation of total energy in order to simplify rho dE dt, which is in this term, and introduce the divergence of the energy flux. So this is done. We have now minus divergence of QE. And now one can identify rho dV dt and use the momentum conservation equation to introduce minus the divergence of the momentum flux. Let's do that. Here we are. Divergence of momentum flux, divergence of total energy. And now we want to create this divergence term. So how to do that? The usual recipe. We use the product rule everywhere. We have a product. So let's start with V divergence QV. V divergence QV becomes divergence of QVV minus QV colon gradient V. Second, we apply the product rule to this term, T divergence QS. T divergence QS becomes divergence of TQS minus QS gradient T. So we have generated a lot of terms. Several of them are already divergent terms. We are going to cluster them into a single term. We have the divergence of QVV plus TQS minus QE. So what are we going to do now? As usual, we want to cancel out the contribution of the divergence term. And we can do a simple choice here and set QVV plus TQS minus QE is equal to 0. This for sure will cancel out the contribution of this divergent term. And it has a consequence to formulate the energy flux. So with this, we can formulate the energy flux being QVV plus TQS. Now, let's look again at these different objects that we have in this equation. The energy flux, you should remember that this is a vector, so it has several components. Here we do it in 2D, but it's working also in 3D, don't worry. So let's spell out QE, it's a vector, it has an X component and a Y component. Now here, TQS should also be a vector. So QS is a vector, TQS, T is a scalar, so TQS remains a vector. Now here we have V. V is the velocity vector, so obviously it's a vector. And now, what about QV? So let's think a bit. What is QV? This is a vector, this is a vector, so QVV should also be a vector. Okay, QVV should be a vector. And since V is already a vector, what should be QV? QV has to be a tensor. So it will have in 2D 4 entries. And the product of this tensor times the vector V here will lead to a vector. So this is a matrix vector product. You obtain a vector out of this product. So QVV is a tensor in the following derivation. So we have to be careful with this. Then we also have terms like QV colon divergence V. So first, this is gradient V, sorry. So first we have the gradient of a vector. What does this mean? The gradient of a vector is also a tensor. So if we make gradient V, we get the velocity gradient tensor. In 2 dimensions, it has 4 components. And now, what is this tensor-tensor operation? We have one tensor on one side, another there, and we have 2 dots. This here is the double contraction. It's the equivalent of a scalar product, but for tensors here. So QV colon divergence, gradient V will give you a product, a scalar product, which can be formulated this way, using these components here. You see this is a scalar now. So we have to be careful now, because we have objects which are different. Okay, QV and gradient V are both tensors. So QV colon gradient V is a scalar value. So let's go back to the entropy production. Let's start with this equation again. We have simplified now the divergence term, so we've left with P divergence V minus QV colon gradient V minus QS times gradient T. We want to make this positive. Let's start with what we already know. remember Fourier's heat flux. Let's make the entropy production, the entropy flux proportional to Fourier heat flux. So Fourier heat flux is minus kT gradient T, and we make Qs is Q Fourier divided by T. By doing this, we generate the term K over T times gradient T square. If T and T are positive, this term is positive with the plus sign here. This is a positive contribution. Now, we have to take care of this term. P divergence V minus QV colon gradient V. What about that? We need to select QV, the momentum flux, such that QS will be larger or equal to 0. And I can tell you already that we will see two cases here, one where the entropy production is 0 and one where the entropy production is positive. Let's start with the simplest case, where QV is equal to pressure times identity matrix. What is pressure times identity matrix? It's simply P on the diagonal. So we build an object which is P on the diagonal. If we take this term here, P divergence velocity minus QV colon gradient V, where QV is P times identity matrix, we end up with such operation here. P, this is the divergence operator applied to the velocity vector. So that's the whole term here. And here we have the double contraction of P times identity times the velocity gradient tensor. And what we're going to show is that this is equal to 0, actually. So you can do the algebra and do all the operations that were stated before, and you will realize that you get P times divergence of velocity minus P times divergence of velocity. This is equal to 0. So in this case, we have a 0 entropy production from the mechanical terms here. If QV, so the momentum flux, is simply P times identity matrix, then entropy Qs coming from the mechanical term will be 0. This is possible, and that's, for example, the case of Euler equations used for acoustics, for example. Now let's study a second case where the term here will generate a positive entropy production. One possible form of the flux is to, as before, have P times identity matrix minus eta times gradient of velocity. Here, eta will be a viscosity factor, so it will be positive. The minus sign is there to cancel out the minus sign which is in front of QV. And the divergence of velocity, the gradient of velocity is there to generate the square term. So let's do the operation here. We have this tensor times this tensor, and the double contraction of this tensor will give you only positive terms. So you will have eta times dvx dx square plus eta times dvx dy square, and so on. So this operation will give a positive contribution from this term. This is by assuming that the momentum flux is Pi minus eta gradient V. Now we have positive entropy production, and in fact, what we've been using here, we've been using a proportionality relation between shear stress and velocity gradient tensor and the factor of viscosity. So this is Newton's law of viscosity. Viscosity is unit Pascal times second, and velocity gradient tensor component is 1/2. So now we have a new expression for the flux, and this flux applies to viscous fluids. One can go a bit further with this expression, and in fact this expression of the flux can be further simplified as QV is equal to P minus tau, where tau will be the deviatoric stress. There is a few steps to go from this expression to that expression, and that is made in detail at the end of this lecture. So keep in mind now that QV is equal to P minus tau, the deviatoric stress. So QV has pressure and deviatoric stress in the same expression. So the resulting entropy production function is TQS is equal to eta times deviatoric strain rate square plus K over T times gradient T square. And this, thanks to this formula here, can be further expressed as tau, the deviatoric stress tensor, double contraction, deviatoric strain rate tensor, plus K over T gradient T square. So what can we do with this expression so far? Not so much, because we don't yet have expression to evaluate how T, P, and V, beware here it's a vector, evolve over space and time. So let's derive equation for the evolution of P, V, and T. Let's start with the pressure, and here we will start with the mass conservation equation. So we have 1 over rho d rho dt plus divergence of velocity equals 0. And we are going to use one relationship, which is an equation of state, which is pressure and temperature dependent. So first thing, we can introduce the equation of state, and we get beta equals beta dp dt minus alpha dt dt equals minus divergence of velocity. And one can isolate the terms beta dp dt on the left hand side, and we end up with this equation, minus divergence of velocity plus alpha t on the right hand side. We are basically done. We already now have an equation for the evolution of pressure with time and space. So we have, on the one hand, the material derivative of P, the variation of volume here via the divergence of the velocity field, and a thermal divergence term coming from the equation of state here. Let's derive an equation for the velocity. So we have to keep in mind the expression for this momentum flux, P times identity matrix minus tau. We are going to use the conservation of linear momentum. So we have rho dv dt is equal to minus divergence of qv. But remember, qv is a tensor here. We can introduce this formula. So we have the divergence of tau minus p times I. Or we can now expand it a bit. It would be divergence of tau minus gradient p. Now we are done. We have a density times acceleration on that side. So this will allow us to predict the future value of velocity. That's basically the inertial term. Now we have the divergence of the deviatoric stress tensor on the right hand side and the gradient of the pressure with the negative sign. So again, I have to insist that V is a vector, tau is a tensor here. So one can make a 2D example for this equation, so we can simply formulate them. We will have rho dvx dt is equal d tau xx dx plus d tau xy dy minus dp dx for the x component. Now for the y component of the equation, we have rho dvy dt equals d tau y dy plus d tau yx dx minus dp dy. This is how to formulate this equation for 2 dimensions here. This expression we can further use test the different fluxes we've derived before. So if we assume that QV was simply P times I, we would end up with this expression, rho dV dx equals minus dP dx. Here, we are reaching a limit, which is the limit of the equations of Euler. In the second case, if we include the viscous contribution and the deviatoric stress, basically, but we neglect the inertial term, so we are going to kill this term here, we can end up with the Stokes equation, which can be used for viscous flow and are very much used in geodynamics. Last but not least, we need to derive an equation for temperature. So these are the different formula that are going to be used, and we are going to start from the Balanced law of entropy. So first thing first, we are going to use the differential of entropy here. So we are going to introduce Cp over T dt dt minus alpha over rho dP dt. Second step, we introduce the Balanced law for entropy. We introduce the source term for entropy, Qs. So these are the two terms here, minus Qs over T gradient T, minus 1 over T, tau, epsilon dot. And note also I put the term alpha dP dt on the right-hand side. Now we multiply everything by t because we had a lot of divisions by t. So the divided by t will disappear here. Now we have a multiplication by t in front of the divergence of the entropy flux. The division by t disappears here and disappears here. T now appears in the adiabatic heating term. As usual, we use the product rule, so we can identify that minus T divergence Qs minus Qs gradient T is nothing else than divergence TQS. And we can now introduce the entropy flux minus KT divided by T gradient T, and this will generate this term here. Let's go a bit further and do an optional step again. In the event K would be a constant material property in space, which is mostly not the case, one can factor out K out of this in front of the differential operator, and this gives rise to the Laplacian of temperature. Anyway, this is the final temperature evolution equation. We have a temperature rate. We have a Laplacian of T. We have the dissipational heating term. So that's the term that's responsible for the conversion between mechanical work and heat. And that's the adiabatic heating term, which we already had in the previous derivations. So altogether, we have the equation for the evolution of pressure proportional to the divergence of velocity and the thermal divergence term. We have an equation for the evolution of the velocity field. Again, this is a vector and this is a tensor, so in multiple dimensions we're solving for each component of the velocity vector with this equation. And we have an equation for the evolution of temperature, which features a Laplacian term, a dissipation term, and an adiabatic heating term. Some common simplifications which are often made is, for example, to neglect inertia. You know that in geodynamic system, over the long term of plate tectonic processes, the inertia may be negligible. So in this case, one can remove it from this equation. Another common assumption is to neglect volume changes. In this case, we end up with an incompressible mass conservation here. So we simply have divergence of velocity is equal to 0. And of course, all other terms related to density variations may vanish. So here, for example, I remove the adiabatic heating term. So this set of equations is now built on the conservation of mass, momentum, and the production of entropy, and uses knowledge from Newton's law of viscosity, and Fourier's law for heat transfer. With these equations, you can solve for geodynamic problems such as subduction initiation or the evolution of continental margins during collision, or the formation of rifts, and study how what is the thermal impact of rift and the interplay with deformation and sedimentation. Or you can even study convection at the global scale. This is the end of the lecture. I hope you've enjoyed the derivation of these three equations. As mentioned earlier, I want to give you some extra material to show you how to formulate the momentum flux from the expression P minus eta gradient of V to P minus deviatoric stress. So let's start with the entropy production term that we've produced earlier in the lecture. We have these three terms here. And what we are going to do, we are going to focus on this velocity gradient. The velocity gradient can be split into a rotational part and an irrotational part. The definitions are given here. The irrotational part is the strain rate tensor that can be written as a symmetric tensor function of the velocity gradient itself. And the irrotational part will be an antisymmetric tensor W. Now we go one step further and we split the total strain rate here into a deviatoric strain rate and the volumetric part. So 1/3 of the divergence applied to the diagonal of a tensor, the identity matrix. Now we are going to substitute the expression QV is P minus 2 times eta times deviatoric strain rate. So we enter this expression here and we are going to check the contribution of each of these terms. So we have 2 terms here in brackets and 3 terms here. We are going to do all the combinations. So let's start with P times deviatoric strain rate. This has to be 0 because deviatoric strain rate has a trace which is 0 by definition. P times divergence of velocity is indeed P times divergence of velocity. So that's one term which will be non-zero and important to keep in mind. P times W will be 0 because the trace of W is 0. So this term now cancels out. Now we start multiplying this term by this term. So we have 2 times eta times deviatoric strain rate times deviatoric strain rate. This gives a positive contribution. 2 eta times deviatoric strain rate square. It's a term to keep in mind. It's the important one. We can do 2 eta times the volumetric term. This will be 0 because the trace of the deviatoric strain rate tensor is 0. And the last term will be 2 eta times epsilon dot prime times W, and this has to be 0 because W is actually antisymmetric. So all the terms produced by the double contraction will cancel out. So what we are left with is P divergence V minus P divergence V plus 2 eta times epsilon dot prime square plus this additional Fourier term. So we can simplify the equation. These terms will cancel out and we will be left with TQS is 2 eta times divergence deviatoric strain rate to the power 2 plus K over T gradient T square. The last step to be done is to use the definition of the deviatoric strain rate. This is tau equals 2 eta times epsilon dot prime. So we can substitute it here, we can substitute it there, and what we will be left with as a contribution in the entropy production is the double contraction of tau times epsilon dot prime. Thanks a lot for your attention.